the last chapter, we studied airflow characteristics of VFD and non-VFD driven air handlers in a data center. In this chapter, we'll try to better understand airflow impedance and find ways to minimize it. As an electrical engineer, I look at airflow as an electrical circuit. Pressure creates airflow, like voltage creates current. Electrical current is controlled with voltage and resistance. Similarly, airflow at different locations in a data center can be controlled by changing pressure and airflow impedance. Let us look at a data center that has 4 rows of server racks and 2 cracks. This is the same example that we've considered in the last session. We'll study the airflow at a tile at the far end as in the figure. The airflow reaching the tile travels an underfloor path from the crack output to the tile. This path offers the airflow impedance Z. The electrical equivalent of the airflow in the room looks as shown. There are 2 batteries representing the 2 cracks. The total impedance seen by airflow at the tile is the sum of underfloor impedance Z in series with airflow impedance of the tile ZT. Q, the airflow reaching the tile, is significantly affected by the net impedance. The resistance of a wire is represented as resistivity of the material times the length of the wire divided by its cross-sectional area. A similar model can be used to represent airflow impedance. The impedance is directly proportional to the length of the airflow path and is inversely proportional to the cross-sectional area of the flow path, which is primarily determined by the underfloor depth. From here, it is clear that the way to minimize underfloor impedance is by minimizing average length of flow path and maximizing underfloor space. In the equivalent electrical circuit as shown here, assume the batteries representing the cracks generate 10 volts and the net resistance is 10 ohms. The current through resistors will be 10 volts divided by 10 ohms equals to 1 amp. The equivalent resistance the battery sees is V by I, that is the ratio of voltage and the current drawn. Here it is 10 volts divided by 1 amp equals 10 ohms. If we replace the simple grated tile with a fan-assisted tile, it acts as an air mover that helps the crack fans. The pressure created by the fan-assisted tile is in the same direction as the crack fan. The pressure across the underfloor impedance is the sum of pressures created by the crack fan and the fan-assisted tile. We'll see how this changes the effective impedance as seen by the crack fan. The equivalent electrical circuit of airflow with the grated tile is shown here. The effective resistance as seen by the batteries is voltage by current. Now, the same circuit with a fan-assisted tile offers higher voltage across the resistance. If the added voltage is 2.5, the net voltage seen by the resistance is 12.5 volts. 12.5 volts over 10 ohms create a current of 1.25 amps. The effective resistance the 10 volt battery sees is 10 volts divided by 1.25 amps, which is 8 ohms. That is, the battery experiences a lower effective load resistance. A lower effective resistance generates a higher current. Let us see how this applies in the airflow domain. We will revisit the pressure airflow curve of 2 VFD-driven crack fans as we studied in the past session. When the cracks are running at full speed, it has the fan curve shown in the figure. When we superimpose the curve of the effective impedance, the operating point becomes clear. The airflow achieved at full fan speed is Qmax. If the amount of airflow required to cool server racks is lower than Qmax, the VFD fans can be modulated to change the fan curve to achieve the necessary airflow. Here, the right amount of airflow is delivered at a lower fan pressure, thereby saving fan power. If a fan-assisted tile is used, the pressure created by the tile lowers the effective airflow impedance. This enables lowering of crack fan speed further to achieve higher power savings. Usually, airflow in a data center is controlled around the hottest points. If airflow at these hot spots can be controlled to manage temperature, airflow at the rest of the room can be lowered and significant energy savings can be obtained.